How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at reaction mechanisms. So our objectives will be to identify catalysts, intermediates, and overall reaction given elementary steps for a reaction, as well as describe the molecularity of chemical reactions given their elementary steps. So reactions don't have to happen all at once, turns out. So if this is our complicated reaction, right? We got a bunch of stuff's happening, bonds are being broken, new ones are being made. It can occur in different steps. It doesn't have to happen all at once. So instead, maybe it happens in a couple of steps. And you can see, this is, let's call that step 1. We'll call this step 2. When you combine the like terms and cancel out what you can, you get the overall reaction. So here, let's see. All right, well, I got MoCO5 here and here on opposite sides of the arrow. I think that's pretty much it, right? You can see, hey, I have my overall reaction now. And how did it happen? Well, it didn't happen all at once. It happened in multiple steps. So that is the whole point of reaction mechanisms is that it doesn't have to happen all at once. So these steps we call elementary steps because it's just a basic, simple step. So step 1, step 2, we call those elementary steps. So here's an analogy. How are reaction mechanisms like cooking? Well, you're going from start to finish, and it takes multiple steps. Some steps take longer than others. Both of those are true for mechanisms in cooking. And when you go through all the steps, you end up with your product, right? So that's true for cooking and reaction mechanisms. So let's take a look at these elementary steps. Intermediates. So if something is created and then used up, we call that an intermediate. So in our reaction mechanism, you can see that, hey, we made MoCO5, but then we used up the MoCO5. So it's not in the reactants, it's not in the products, it's an intermediate. It's in between the reactants and the products. We made it in one step, but then we used it up in a second step. So those are intermediates. So cooking analogy, it's like making quiche. I don't know if you've ever made quiche, but one of the important steps is you got to shred zucchini. So you got to get some zucchini, you got to shred it, but you don't end up with a side of shredded zucchini. You use that shredded zucchini to make your final quiche. It's not there as a pile of shredded zucchini. It's an intermediate. So you made shredded zucchini, but then you used it up. It's your intermediate. So catalysts. Catalysts are used initially, but then are reformed as products, right? We know that catalysts speed up reactions, but they aren't consumed by them. So they're there when we start, and they're there when we finish. So ultimately, yeah, that's what I just said. It's there in the beginning, it's there at the end again. So if this was my reaction mechanism, you can see, hey, I'm using up OH minus, but then I'm producing OH minus. So the OH minus that I used, I ended up remaking. So the OH minus isn't consumed at all. It's not a reactant, it's not a product, but it was involved. So there you go. So cooking analogy, maybe it's like a muffin tray. If you're baking some muffins, you use a muffin tray, but it doesn't get used up. You get to reuse that muffin tray. It's there at the end, right? When you're done baking, you still have a muffin tray, but you needed it for the reaction. So molecularity of elementary steps. So it's just basically describing how many molecules are involved in that step. So if my step only used one molecule, we call that unimolecular because it's got one molecule. If that elementary step had two molecules, we call it bimolecular. And they don't have to be the same molecule. You can have A and B, that would be bimolecular. You could have two A's, that would be bimolecular. Or you can have termolecular, where you have three molecules involved. So again, they don't have to be the same molecule. They don't have to be different molecules. It's just three of them involved in that one step. So you can see how it affects the rate law. So for unimolecular, it's just first order, bimolecular, second order, termolecular, third order. So here's the thing about termolecular reactions is they're pretty uncommon. So why do you think that is? Well, let's take a look. Here I have a unimolecular process, I have a bimolecular process, and I have a termolecular process. Which one do you think is the least likely to occur? Well, in unimolecular, I have one molecule reacting all on its own. Bimolecular, I got to get two atoms to collide with each other in the right orientation with enough energy. And termolecular, we got to get three molecules to collide at the same moment in the correct orientation with enough energy. So why do you think that's going to be uncommon? Well, that's the least likely of all the possible things that we're talking about. You know, 2 things colliding with the right orientation, enough energy is one thing, but having 3 of them collide at the same moment, at the perfect orientation with enough energy is the least likely of all the processes. So they're uncommon. All right, so the mechanism for formation of the product X is given to be the following, right? So here's some things you need to be able to do. What is the overall reaction? What, if any, intermediates exist? What, if any, catalysts exist? And what is the molecularity of each elementary step? So let's start with what is the overall reaction. You got to look to see if there's any intermediates. So in step 1, we're making substance D. And in step 2, we're using up substance D. So these arrows you can treat like equal sign. So I have a D on the product side here, and I have D on the reactant side there, so they're going to cancel out. So what I really have is Y plus B gives me X, right? So everything on the left side of the equal sign should be on the left side of the arrow, and then vice versa for the right, right? So that's what I got, right? So what, if any, intermediates exist? Well, substance D is an intermediate because I make it in the first step, but I use it up in the second step. What, if any, catalysts exist? Well, let's see. Catalysts are there in step 1, so it's used in one step and made in another. Do we have that at all? It doesn't look like it. So none. We don't have any. And what is the molecularity of each elementary step? Well, this step would be bimolecular. And this step would be unimolecular. So in that first step, we have 2 molecules coming together, and in the second step, we only got the 1. So there you go. So I challenge you, try this one on your own and then check. All right, so what is the overall reaction? Well, let's see. We have, I'm making B here. I'm using it up there, so I know that's going to drop out. I have D on the left side and on the right side, so they're going to cancel out. So what I end up with is 2Y gives me X. All right, so that's the overall reaction. So what, if any, intermediates exist? Well, B I made in the first step, but I used it up in the second step. So substance B is going to be an intermediate. What, if any, catalysts exist? Well, if you see, D gets used up in the first step, and then it's made in the second step. So we use it initially, but then we remake it. So D is going to be our catalyst. And what is the molecularity of each step? Well, both of these steps are bimolecular because they both have 2 molecules involved. There you go. So summarize. Can you identify catalysts, intermediates, and overall reactions giving elementary steps for a reaction? And, can you describe the molecularity of chemical reactions giving their elementary steps? I hope so. All right, cool. Okay, bye.